In the second part of our lesson, you should have an understanding now of precipitation reactions, where you've got two ions reacting to form a solid. The other piece we want to look into today are acid-base reactions, and these also are going to be double replacement reactions. We're going to review neutralization reactions and also titration. And we'll get into acids and bases in a lot more detail in the third NIMAKES, and you will absolutely love acids and bases because they are so fun. All right, the first thing we want to do is review some basic definitions. Arrhenius acids and bases and Bronsted-Lowry acids and bases. So let's take a look here. Let's think back to honors in regard to the Arrhenius definition. Thank you. In regard to the Arrhenius definition, what is an Arrhenius acid?
Is it like the ones that if the base you lose, you gain an H plus, and the acid you lose one?
That's the Bronsted-Lowry.
What's the other one?
It's the one with the like they add up, or like you add an H.
That's the Bronsted-Lowry.
Just said.
That was the one.
Right. The Arrhenius acid generates what? That's the Bronsted-Lowry. Either a proton or a hydronium ion.
Oh.
So for example, if you had hydrochloric acid, the solvent has to be water. You generate proton, or you could show it this way. Where you generate hydronium ion. So the generation of proton or hydronium ion is indicative of an Arrhenius acid.
I was never taught I could use that, just the proton.
If you have an Arrhenius base, you're going to generate what?
Hydroxide?
Yep, hydroxide ion. So for example, sodium hydroxide generates hydroxide ion. You could have a group 2 strong base, and you would generate hydroxide ion as well. Now, what many of you were referring to initially, because you love the conjugates, is the Bronsted-Lowry definition. And here, an acid is a proton donor or acceptor? Donor is correct. And the base is a proton acceptor. So for example, if you had this substance reacting with ammonia, the acid is a proton donor. It will donate its proton to the base. Go ahead.
Will we Cl the chloride ion plus ammonium, but it'd be like plus another H?
Yeah, ammonium ions, correct.
Isn't it CO2?
That's ammonia. Ammonium.
That's okay.
This is an ion.
But it's
Ion, ion, ion. No subscript there. Ion. It's not chlorine gas. This is the conjugate base of this acid. this is the conjugate acid of this base. So acids are proton donors, bases are proton acceptors.
Can't ammonia be a base and a acid?
It can be, but in this case it has to be a base because with hydrochloric acid, you probably will recall that in almost every case, with the exception being water or ammonia, the anion charge indicates the maximum number of protons that can be accepted. So hydrochloric acid cannot accept a proton because then you'd have two, and that's more than the charge predicts. You may remember it more clearly here. So you're typically not going to have more protons than the charge predicts. Water and ammonia are an exception, and you are correct. Ammonia is a base in this instance, but ammonia and water are what we refer to as amphoteric or amphiprotic, and they can either accept or donate. They have that ability. Okay. The other thing I want to just review with you is some acids are strong and others are weak. Now this is not based on the concentration, but rather whether the acid ionizes completely. So strong acids ionize completely, and they are excellent conductors of electricity. They will illuminate that light bulb. With a strong acid such as hydrochloric acid, you will only show the forward arrow. It ionizes completely such that whatever the concentration of the acid is the concentration of the proton, and you could determine the pH in that regard. Most acids are not strong but rather weak, and they only ionize partially. For example, if you have acetic acid, an example of a carboxylic acid with that Cu group, this is an equilibrium reaction. And so you've got that forward and backward reaction. And actually, if you consider acetic acid a weak acid, equilibrium actually lies far to the left, such that these two concentrations are not equal. You have much more acetic acid as a unit than you do proton. Ionization is pretty minimal here. In honors, not in my class, probably not Regula's class, but I know Mrs. Vera did do some work with you with Kas and Kbs, so you would have seen this in a little more detail than some of the others. We're going to touch that in the third 9 weeks, and it might be very nice for you to recognize it because that is a very difficult concept. Now, some acids are polyprotic. They can donate more than one proton. You see that with sulfuric acid, but we'll focus on that later in the year. I'm not concerned with that concept at all. Typically, the ionizable proton is the one in the front. However, if you have a Cu grouping, the ionizable proton is in the back. So just have a recognition of where it might be. There are 8 strong common acids. 3 of them are binary, comprised of 2 elements only, an H and a nonmetal. Hydrochloric acid, hydrobromic acid, hydroiodic acid. There are 5 oxyacids. 1 is diprotic. Nitric acid, sulfuric, perchloric, chloric, and periodic. You want to be familiar with your strong acids as you were in honors. Strong bases. Your group 1 hydroxides are strong bases. They too ionize completely. With your group 1 hydroxides, the concentration of the base is equal to the concentration of the hydroxide. You can see some of your group 1 bases here. There are 3 strong group 2 bases, calcium, barium, strontium, CBS like the TV station. Be careful there though, you do get 2 hydroxide ions for every 1 mole of calcium hydroxide, as we mentioned earlier. Weak bases don't ionize completely. When you react a weak base such as ammonia with water, you get the conjugate acid and you see the hydroxide ion generated. So weak bases react with water and generate hydroxide ions. Another weak base, and you typically see this with your amines, is methylamine, reacting with water here. We'll worry more about that conjugate aspect later in the year, but your acid-base reactions will come into play here, which is why I mentioned them, and we'll get to that in the neutralization piece. The other type of reaction that I do want to mention to you here, this is a synthesis reaction, and we'll review this in the synthesis section, but I'll mention it here because you're generating acids and bases. If you have a non-metal oxide, so something like sulfur is a non-metal hooking with oxygen, when it reacts with water, it forms an acid in every case. And these, for the most part, are very easy to predict, with the exception of the second one listed here. Sulfur trioxide in water makes sulfuric acid. Now, sulfuric acid is a strong acid, so we would ionize that as follows. I'm not very concerned with that one anymore. It's really very difficult, and they seem to have moved away from it. Dinitrogen pentoxide in water form nitric acid. Again, nitric acid is strong, so we would ionize that. I'll give you an example in a minute. Carbon dioxide in water form carbonic acid. So a non-metal plus oxygen, a non-metal oxide, will make an acid. A metal oxide in water always makes a base. If the base is strong, you would ionize that as well. Let's take a look at several examples. It's nice to have examples written out for you, but it's also really helpful to see it in action. For example, we'll take a look at several examples. Now these substances are gases, these substances are solid. You're not going to bust up a gas or a solid. And this is all liquid water. Excuse me. Thank you.
What does the second one say? Gas or solid?
Gas. Nitrogen dioxide is a gas. Okay. A non-metal oxide plus water is going to make an acid. It's sulfurous acid, a weak acid. We leave it as a unit. That's sulfurous acid.
Wait, how come it went from SO2 to SO3?
Remember the extra O from the water?
Exactly.
Okay, thanks.
How do you know that it's aqueous?
It's an acid.
Oh, that's true. Well, not all. Yes.
This one, and as I said, with the exception of that tricky one that was in there, for the most part, you get the O with the O's, and the H's go in front, but formula write properly here. Now that's not balanced, so what do you need to do?
You add an 8.
We have a 2.
You want to put a 2 here
And a 3 and
and a 2 here?
that.
2.
Oh yeah.
Are you balanced? No.
You need a 2
And
in
a 2 in
front
front
of
of the
water.
H and then make it a.
That's not going to balance it either, is it?
Yeah, put a 2 in front of the H2O and then make the other 2's 4s.
That's not going to do anything.
You have 3 O's on the left and 3 O's on the right.
No, you have
Yeah.
to
Is it
balance
balanced on the
No.
Except with the 2, is it
No, without the coefficient, you have 3 O's on the left.
It is. Wait.
No,
It's not balanced.
The H is
Oh,
not
yeah.
balanced.
Yeah, the hydrogen's only on.
So what are you going to do?
I'd say put a 4 on all of them.
It's not going to work.
All of them.
All right, we'll balance this one in a sec. The other point I want to make is that nitric acid is a strong acid, right? It is. And so you wouldn't write it all together. You would write it this way, which may actually help with the balancing.
Yeah.
Yeah, the
Waiting.
nitrate needs a 2 and the nitrogen dioxide needs a 3. Oh, wait, that's
No, you're not
not
going to do a 2 and a 3 because that's not going to balance. We'll balance it at the end. Do you understand that the strong acid ionizes completely, so you break it up? We'll balance that one at the end, don't worry. Looking at this one, we have a metal oxide and water. We don't generate an acid, we generate a base. Magnesium hydroxide, a weak base, we leave it as a unit. Sodium oxide and water, what are we going to make? Sodium hydroxide. But is sodium hydroxide a strong base?
Yes.
Yes, so we do this.
That was not balanced.
No?
Okay, put a 2 in front of the hydroxide. Oh, you already did it.
Well, wait.
Yep,
Can we balance the other one?
yep.
I don't understand how to balance that.
You just put a 2 in front of
This would have been sodium hydroxide, this is magnesium hydroxide.
Yeah, just put a 2 in front of the H and it's balanced.
No, it isn't.
No, it isn't.
How?
Put in 4s. Well, yeah, it is.
But I'll tell you why it isn't.
No, the charges.
Because the charges aren't balanced. You would have a charge here.
So then you have to put a 2 in front and a 3.
Yeah, but then you
Can't
can't
do that.
But then it makes everything.
Can we just skip it? Just not have to throw out this question.
Okay. We'll address this one
It's
later.
like a balanced equation for the.
Is it possible?
We should Google it. Do you,
No, we're going to do it at the end. We're going to leave it hanging. We're going to do it at the end. It's not hard. You guys are just making crazy stuff hard.
so can you do
Wait,
it?
All
can
right.
you write the names of the other
Can
acids?
you do it there?
This
There
is
are no other acids.
nitric acid. This is a base.
She was trying to spell base with M-A-C.
Wow.
And this is sodium hydroxide.
Bag base.
Thank you.
You take a break.
How did you know there was going to be a hydroxide?
Here,
Yeah.
because a metal oxide plus water always generates a base. All right. The other thing we want to talk briefly about today, and this is just review, is neutralization. It's so easy. We're going to keep it simple. With neutralization, we have an Arrhenius acid and an Arrhenius base generating salt and water. Typically the salt is neutral, but not always.
It can be basic, right?
It can be basic or acidic depending on what salt you generate, but that's beyond the scope right now. We'll get into that in acid and bases. So you've done this before. You have an Arrhenius acid and hydrochloric acid plus an Arrhenius base making salt and water. A net ionic equation for a strong acid, strong base will always be the generation of water from proton and hydroxide ion. This piece of the puzzle here, we are going to skip right now. I'm going to gamble because we're not going to need that until acid base, and it just gets to be too hard. So let's keep it simple. In regard to titration, this is something I do want to review with you. It's something that you are going to be extremely good at this year, and you will be titrating multiple times in the lab, and they most likely will be your favorite labs because they are cool and they are the most fun. With titration, titration is a way to determine the concentration of an unknown substance, typically an acid or a base, although in your first lab, you're going to be determining the concentration of a base and then using titration in a redox reaction, which will be new to you and we will get into next week. Very brief video on titration. I will illustrate titration for you in terms of calculations in a few minutes. And before we do our lab, I'll titrate for you so you can see it. 1 minute quickie video.
A titration is a controlled acid-base neutralization reaction. 20 milliliters of hydrochloric acid of an unknown molarity is added to a flask.
Now what you add to that Erlenmeyer flask is called your analyte. You don't know the concentration of that.
Drops of indicator dye are added to the acidic solution. This indicator dye is clear in acidic solution and pink in basic solution. The burette is filled with a sodium hydroxide solution of known strength and an initial reading is taken. The base is added to the acidic solution until the solution stays a slightly pink color. At this endpoint, a final reading is taken.
I do want to make mention of one thing because this was on the AP exam not last year but the year before. This digit that you are guesstimating from a burette has to be a 5 or a 0. So this is a problem in this video, okay? And when we do it, I'll illustrate that for you in more detail.
The moles of base added equal the moles of acid present.
And that's an important concept too. You're going to see that the moles of acid and base are in stoichiometric proportions.
Reaction can be followed using a pH meter instead of an indicator dye.
And we'll be doing the pH aspect of it later in the year.
Can we finish the video?
Nah, because it's going to, I'll finish it for you if you want, but it's going to be confusing.
Initially, the pH changes very little as base is added. Suddenly, the pH changes rapidly as the endpoint passes. The solution quickly becomes very basic, and again, the pH changes very little. The endpoint occurs at this middle point on the curve.
And that's something you'll be doing in the lab later in the year. You'll be generating pH curves, and I do it through Excel. It's really kind of cool. We could do it through Google Sheets as well. Your goal here is to determine the concentration of an unknown substance. A burette is that long glass tube. It looks something like this, and we'll have these set up next week for your lab. They're very fun to play with.
Stop.
It's not, it's a
Stop.
stopcock.
Stop.
It's graduated so you can read it. The solution that goes into the burette is known as the titrant. The other solution in the flask or a beaker is an analyte. The equivalence point is when you have stoichiometric proportions of acid and base. The end point is the color change, and we'll go through that when we do the lab. Just as a refresher, in order to do a titration problem, you're going to write your balanced equation. You'll calculate millimoles of the substance you know both the concentration and volume of. Stoichiometrically, you'll get millimoles or moles of the other, and then you can calculate either the molarity or the volume. We're going to do this first example together. It should look like something from honors. You can try this one. We'll do this one together, and you'll have one problem that you want to work on at home. Let's do this first example together. My approach here is always to get the information out of the problem, first in the form of an equation, and then with the quantities provided. In this problem, and I always write the acid first, it's the way I was trained, you're going to have sulfuric acid reacting with sodium hydroxide. An acid and a base react to form a salt and water. That's a double replacement reaction, an acid-base reaction of an Arrhenius acid and an Arrhenius base. In regard to the amounts or quantities provided, we've got a concentration of base of 0.5 molar and a volume of 32 mils. We've got 24 mils of sulfuric acid, unknown concentration to begin. So my first step is to write the balanced equation and to write the information down about the two reactants. For the substance, you know both the concentration and molarity of, the concentration or molarity and the volume. I'm going to go after millimoles because they gave me a small quantity. So millimoles of base here is half molar times 32 mils, and 1/2 of 32 is 16 millimoles of base. That's the second step. In the third step, stoichiometrically, you can go from millimoles of base to millimoles of acid, and then in the last step, you can get the concentration. How are we going to get the concentration of sulfuric acid?
Moles to grams.
You're going to divide by the volume. So you have 8 millimoles, and you're going to divide by the volume of the acid, and without a calculator, 8 over 24 is a third, so you have 0.333 molar sulfuric acid. And there's nothing different there than what you would have learned in honors. Very straightforward.
I had learned this in honors.
So 4-step process. If this is new to you, keep those 4 steps in front of you now as you work through the problem on the screen, which is in your notes, highlighted in yellow. Give it a shot.
much of that is work.
That's good.
Yeah. Yeah, go ahead. Well, Ethan, hang on though. I have a few things I want to hand out. Just give me 1 sec.
So water is gonna use the H from hydrochloric acid and the hydroxide to end up with calcium iodide.
Because it's hydro. If it's hydro, it's binary. Hang on.
I have no idea. Okay, now how can I concentration? Wait. Apart from neutral. Okay, so we have. So what is hydro potassium?
Some practice.
You just asked me to find a car.
Is it H2I?
So you use this OH to make the water, right? So then you have the calcium.
Oh, that's the key.
Wait, is it? What's hydrochloric acid?
This side.
I just. Wait, then what?
HIO3 is
I just read the first time it said iodic acid, the second time I thought they were two different things.
Not 4. Not 7.
Wait, you got.
This one's a little different because I changed my mind on this one.
What'd you get for three, right?
calcium iodide and water.
Make sure you come back with a solid understanding, and the one problem that says for homework, you should try and do that too. We're gonna go through the other one. I'm probably gonna have to stop there though.
I can finish it on the video too.
Oh, you can take one, not
Then you'll be about 32 minutes in.
you can take one, not
HI. Some of you are not recalling this, and this is from the summer assignment. You've got to be able to do this with ease. The problem's not titration, it's the formula writing. Here's your balanced chemical equation. Should have gotten that. Raise your hand if you got it. And if you didn't even really get it going, we have a timing issue that needs to be addressed.
Would you have to show work for that necessarily?
As little work as I do is perfectly fine. In a part six, this would more likely be a part one question, so no. Right, and that's like a part one question.
You don't need to write the whole ratio down, you just do, and that's only 100 divided by 2.
Now, I don't expect you to do all of this, so if you give me a sec, I'll tell you what you can do at this point.
Can you show us how to balance that one? It's really bothering me.
Oh, yeah.
I don't think you can.
Hey, Mike and I forgot about it.
I should have an extra of both packets somewhere. Let me know where the extra one is. No, that's different. Ethan got his stuff, so don't drop anything on his desk.
There's only 2 papers, right?
Yeah, one of each. And let me see, I have an extra one here, but I should have one more. All right, in regard to this problem, you should be comfortable with this. I'll explain what I want you to do in the packets in just a minute. Is there an extra one of each of these somewhere? No? Okay. Yours is already marked up. Hang on one sec. Okay. In regard to what's in your notes, we're a little bit behind the other class. You should be able to do both of these problems for next time. I'll pick up here with you, which will limit what you are able to do in those packets, because there's a concept that's addressed here that I don't think you'll follow without instructions. So we'll pick up there next time. In terms of what I've given you for the practice quiz, and are there any extra practice quizzes? No? For the practice quiz, for part 1, you can do 1, 2, 3, 4, and 5. So just highlight 1, 2, 3, 4, 5. You can do all of part 2. And that was like the problem we worked on with the beaker, and there's some stoichiometry built in there. And on part 3, you can do 3, 4, 6, 8,
We can do the diagram one.
Has to be in color.
9, 10. The diagram ones could really be a problem because they are messy. We'll do them in class if need be. 12, 13, 14, 15.
9, 10, 12. Yeah.
Everything except 11 might have been easier to say. All right. On this sheet here, start on page 5, which also says 51. You can do 2. No, you can't. On this one,
I don't have that one.
you can do 3. You can do 'That's it. On the other side, you can do